Okay. Michael's going to talk about hope is the monad.
Yeah, so final talk of the day. There's still people here, so here's a Germanism you can use in your next conversation. But before I speak, let me say a few words on the performance evening in case you don't know about it yet. So today at 7:30, some of the people who've been giving talks at Farm and some other people have organized a concert that is going to happen at Beverly Hills Live House. And the thing is, really, it's a free event for the public. So if you want to be there and you want to make sure that you get a seat, the doors open at 7. And the place has, I think, about 80 seats. So we're assuming that it might get crowded. It's essentially free. You just need to get a 500 yen drink ticket, which you can then, of course, spend on drinks. It's really easy to find. It's about a 20-minute walk. So the main street from the venue downtown goes right past Kintetsu Nara Station. And just before Kintetsu Nara Station, you turn right. I believe this is a 7-Eleven. Not that that tells you much in this town, but so there's a 7-Eleven. You turn right there, and it actually says Live House Beverly Hills in Roman letters. Okay, so don't try looking for kanji or anything like that. So anyway, despite the forward, question.
You said main street. Which of the two main streets did you mean?
So if you just walk down straight from the venue, so I mean, have you seen Kintetsu Nara Station, the big train station?
Yes.
So that's the street that it's on. Okay, so that makes sense. So despite the forward-looking title, this is going to be a retrospective. Many years ago, I became a freelance software developer, and I had this vision that I would improve the quality of the software that I worked on. And I thought I'd made modest assumptions. I would get in at a 3, and I would push things up to an amazing 6, right? And the reality is, as I'm sure you're aware, I was hopelessly young and naive at the time, was more like this, right? And so instantly I was not so happy. So one of those places was what at the time was a very large German bank. So it's no longer German, it's no longer very big, but there it was at the time. And they called me up to tell me that they were doing distributed Monte Carlo simulations to price financial derivatives using a system called Scheme 48, an implementation of the Scheme programming language that I happen to be the maintainer of. So it made a lot of sense to me and to them to hire me. Even though I was a little surprised because Scheme 48 was an experimental system that generated many publications, but that wasn't really intended for production use. And I believe this is still the text that you find on the Scheme 48 webpage describing the system. But I thought that was cool. And just a couple of weeks ago, I got a call asking for a 64-bit version of Scheme 48 because apparently they were still using it. So this was in 2004, quite a while ago. But they'd already done this. The distributed Monte Carlo was already working, so they sent me to work on something else. And I've got some really old slides to tell you about that, but that were very instructive for me at the time. So I was supposed to work on market data. And I don't know how familiar you are with, and Ron is you're just going to have to tune out, I think, or correct me. So if you do pricing calculations, what you depend on is you depend on current market data. And so there's a lot of things that get traded on the exchanges. They generate prices. And there's things that you can find out from those prices. What's especially important in pricing are things called volatilities, which measure how much a given quantity changes over time. And the way it works is you don't usually observe volatilities from historical data, but you sort of infer volatilities from what are very simple financial derivatives called calls and puts, which have a very famous equation that puts them in relationship with the volatility. So, and the thing is, though, there are many different calls and put options for a given financial quantity, depending on when that option expires and what the strike price of that option is. And it used to be the case, I believe, before the early 90s, when no matter what the maturity and the strike price was, you would get sort of about the same volatility. But nowadays, they differ, and so you get entire volatility surfaces. Now, a lot of financial derivatives are not in terms of individual financial quantities, but of baskets of those quantities, where you sort of have a weighted sum of them. And these are not directly traded on the exchanges. So if you want one of these parameters for your pricing process, you need to make them up from the quantities that you actually know. First of all, you might want quantities that are in between the maturities and strike prices that are actually traded, so you do interpolation. And then usually some traders' belief feeds into how they compute basket quantities from their constituents, if that makes sense. And now traders, well, not Ron, but the people with the suspenders, they like to have a portfolio that is robust in the face of changes to the market. So they like to play scenario games. It might be a very simple scenario where an individual quantity just goes up by 1%. You might have a slightly fancier scenario where an entire volatility surface goes up. You might have a scenario where an entire basket goes up, or the entire market or a market segment goes up or down, or something happens to that. And so, I was involved in writing the software that would let the traders specify such scenarios. But unfortunately, I was not like in the scheme corner of the software ecosystem. I was in the C++ corner. And the way things were done there was that they had a class, a C++ class, that represented sources of market data. And this is actual code from the system at the time. So there was a class called market data, and it had methods like get spot, which would get you like the current price of something, or get volatility. Get spot would get an identifier, a number that identified the financial quantity for reasons unknown to me, called a SICOVAM. Get volatility, you would have to specify the maturity and the strike price. Do not ask me why those are doubles. Specifically the date of the maturity or the duration. So I think that was a date, actually. So anyway, but you get the idea. You have an object that is hooked up to the current market feeds, and it will tell you what the current quantities are. Now, as I told you, traders like to play with scenarios. And when they play with scenarios, they want not the actual source of market data. They want something that is like that, but slightly different. And in object-oriented programming, of course, when you do something like something you already have, but slightly different, you just make a subclass and override methods, right? That's how you do things. But the traders, they wanted to do this at runtime. We couldn't have them compile C++ code just to create a new scenario. So people, fortunately not me, were looking for a way to do like dynamic subclassing, if you will. And what you do as an object-oriented programmer is you open a patterns manual, and right there is a decorator pattern. This is from some patterns manual, and says, oh, they are a flexible alternative to subclassing for extending functionality, which seems like a perfect fit. And what I'm about to tell you, I've seen several teams do independently from one another, completely on their own. So the way a decorator works is you create a subclass of the class that you want to extend later. You override every single method with a method that will just delegate to a delegate object. And then when you want to have individual kinds of changes, you make further subclasses where you override individual methods that will perform that modification. And this way you can chain decorators together. And it might look like this. So you would have, for example, like a uniform spot shift for the entire market would look like this. So there's the get spot methods that you saw the declaration for. F market data is the delegate object. You call its get spot method, and then when you've got that, you multiply that by a factor. Unfortunately, the way object-oriented dispatch works out is, well, if you have like a basket or the market, that is going to call the getSpot method recursively, because your basket is also going to be an entity on the market. And each time it goes through that recursive call, it's going to multiply that factor. So you get double and triple shifts depending on how high the tree is that you have. And you wouldn't believe the amount of hacks people put in place to work around that, to detect that you're being called for the second time around and whatnot. And it just, people kept on discovering cases where that didn't work, so they just added more code to catch those cases. And that kind of never ended. And I have to admit, when I first saw that, I was brainwashed. I was coming from functional programming, but I thought, here's a reasonable application of object-oriented programming. This decorator pattern looks nice, until I saw this. Right? And then I kind of remembered that really I'd been brought up to be a functional programmer. So, and what you really need to think about is you have the actual market, and what you're just looking at is you're looking at simple functional transformations of that market. Market goes in, slightly modified market goes out. And this is like shockingly trivial that you just need to have a little combinator model where you have transformations on the market, and there's certain kinds of transformations such as volatility shifts and spot shifts and whatnot, and you just compose them via regular function composition. And this is like shockingly trivial even to implement in C++. It worked immediately, and it solved all those problems we'd had with the old object-oriented model. So, that's a lesson I've remembered many times, probably forgotten many times since. You really, whatever the problem domain is, it pays off to look for like compositional combinator models in them. No matter how profane and real world and trivial things seem. And I've since discovered combinator models in many applications domains. In stage lighting, in financial derivatives, of course, there's that famous paper by Simon Peyton-Jones and Jean-Marc Hébert that you're probably familiar with. Market data transformations I just described, things like access rights, document archives, queries, insurance contracts, whole production routes, tools, scheduling policies, questionnaires, control automata, all kinds of different applications. So that's one of the lessons I want to impart to you from this talk. Yeah, I'll get to that. I'll get to that. Don't worry. Yeah, sure. I'll get to that. There's hope. Anyway, so before I was that freelance software developer, I was a researcher in programming language for quite a number of years, and I guess that was my first contact with trying to put functional programming in production by creating the Lula system, which is a system for stage lighting design and control, which, among other things, contains a compositional model for lighting configurations and also lighting animations in terms of functional reactive programming. And it's kind of an old system. I should have remembered that lesson. That was earlier. That was a long time ago, but the system is still pretty good, and occasionally it actually gets used, and you really know, that your system is reliable when you're willing to go on stage when the computer is sitting there. By the way, anyway, in 2003 I quit university for reasons. Then I was that freelance software developer, and in 2010 I became CTO of a software consultancy, I guess you'd say, called Active Group, and we do software project development using functional programming. And the first project I got into had to do with scheduling for semiconductor fabs. And I don't know about you, but when I came into this, I thought semiconductor production works like, there's a big machine, is what I thought, and you put in a wafer, and there's a lever that you pull and goes ka-chunk, and you pull the wafer out, and the chip is done. And I learned that that is not so. It's a much more complicated process. So here's one original slide I had from that particular client. So I don't know you all knew this before. How embarrassing. So a modern microprocessor takes like 6 weeks to make, and it can take like thousands of production steps. And there's two things. First of all, it consists of multiple layers, and each layer goes through a complex sequence of things that are needed to actually make it. And some of those steps require machines that are cost like $10 million, and so you don't have too many of them. You certainly do not have enough to line up those machines in an assembly line. So what happens is that your boxes of wafers, the lots, go through your fab in complicated patterns. That machine that is the fab is so expensive to run. You really want to make the best use of it that's possible, and so you really need a computer to determine what course your wafers should take through the fab. The details are not particularly important. So not just is it a complex scheduling problem, also a fab is not really a piece of precision machinery. Things, it operates at the level of quantum physics, so things break down all the time. Also things sort of go out of spec all the time, and some of those processes are chemical processes, and they're more like cooking than sort of precision manufacturing, and surprisingly brittle. So when you have a computer system that tries to control the fab, you can't give it instructions. You can sort of give it recommendations, and then, you can see whether the fab executes them or not. So now we're getting somewhere, Phil. You know who that is? Okay. Who knows who that is? A few people. Yeah, no, not a German football player, but in football, there's a thing called penalty kick, right? At 11 meters, somebody gets like a free kick at the goal, and the way the physics work out is the goalkeeper needs to decide what corner or what side to jump to before that particular ball leaves the foot of the penalty kicker. Okay, so you have to hope that it goes where you thought it would, right? So, and that woman is Hope Solo. I think the former, now for a few weeks now, the former national goalkeeper of the American team, not a German. Anyway, so you need to manage that hope, right? You give a recommendation, an instruction to the fab. You hope that the fab is going to execute it, but you need to notice if that doesn't happen. You need to notice when it happens later, and you need to track what happens. If you go on a tour through a modern fab, sometimes your tour guide will point out to a lot, to like one of those boxes, and will tell you, well, that box has been there for 6 months because some production step didn't happen and it just got forgotten. So you preferably don't want that to happen too much. So when I was writing the code to handle that hope, I first thought, well, there's all these kinds of specific situations. You want to hope that indeed a wafer or a box of wafers gets tracked into a particular piece of equipment, that it gets transported to the right place, and so on. And it got very unwieldy and complicated. And that got me thinking about sort of a more general notion of hope. So there's like pure hope, where you can do nothing to make it happen. You just hope that it will happen all by itself. You might give an instruction, like you give an instruction to a fab and say, do this, and then you hope that the fab is going to execute it. Sometimes that will not happen immediately, right? And then maybe you need to notice that it hasn't happened immediately and follow up, something like this. At some point you have to realize that your hope gets shattered, right? And so you can draw a picture that looks maybe like this. It says, well, your hope, it may get shattered, it may get fulfilled, in which case it produces a value, some object, something that tells you about it, some payload. Or that hope might turn into another hope, where you go and follow up on something. And you can easily imagine that there's sequential composition, so some kind of hope, you hope that something happens and then something else happens. There's parallel compositions, and all along you see the fab chugging along, where you issue dispatch instructions and the fab does its thing, right? And of course, this is a monad. So hope is a monad, Phil. Hope that answers your question. So there was a combinator model. We were also thinking on how to make scheduling policies. So the overall strategy that you use to control the fab compositional. And so we were thinking of various aspects of scheduling that we really wanted to separate from each other. Things like the track-ins and the movements of the individual lots, things like plant maintenance of the machines. I'll talk a little bit about queue time violations, just validate the things that you're doing to make sure that you're not applying the wrong production step and therefore destroying a wafer or a box of wafers. And that's kind of materialized with a specific problem called the queue time problem in semiconductor fabrication. And so I told you already that a semiconductor takes about 1,000 production steps to make. And what makes it even more complicated is that you sometimes will have subsequences of those 1,000 steps, of those routes. And when you start them, you have to finish them within a certain amount of time, because otherwise the chemical processes that are going on will destroy the wafer. Okay? So, and that's called a queue time zone. And so the idea is that if you enter a queue time zone, or if you're just about to enter a queue time zone, you need to make a decision. You can either enter it, in which case you risk that it will not make it out in time, or you might want to, if there's congestion going on, or one of the machines that's inside the queue time zone is broken, you might want to delay a little bit and wait for the congestion to clear up, or for that machine to get fixed, or whatever. And so we were thinking about how to tackle that, because no modern scheduling system that's in widespread use handles this problem directly. They all handle it indirectly by hoping that they're just going to speed up the lot or whatever. But when we talk to domain experts, the thing that they always want to be able to do is to just simulate that lot going through the fab, and then just seeing if it will make it out okay the other side. And so that's what we set out to do. Is we're just going to apply simulation, moreover, what we wanted to do is we wanted to track sort of when each step happens during the simulation, so that we could inform sort of the rest of the scheduler when that lot was getting behind, and maybe the scheduler might want to do something about that. So you can easily imagine that this, here's that picture, right? You can see the actual lot getting behind, and then maybe you want to tell the scheduler about it. So you can easily imagine that this implies some kind of nesting. So if you simulate while you're scheduling, then that simulation also needs to simulate the scheduling, and this might nest to some level. And of course, that is not, so whatever you want to call it. In the 80s, we used to call it simulation needs to be reentrant. And you can easily imagine that that is not going to work if the state of your fab, or the representation of that state in your computer, is a big chunk of mutable state. But it's really easy if you're doing everything in a pure fashion, right? It's laughably trivial to do this. So, we came up with this picture where you sort of wrap the queue time scheduler around an inner scheduler. So first of all, the queue time scheduler does something very simple. If the scheduler actually wants to put a lot inside a queue time zone, and that is, the queue time scheduler finds out that that is not a good idea, it will just keep it back, or it will let it go through. But also, the queue time scheduler and that inner scheduler need an interface that allows the queue time scheduler to transmit when a lot is falling behind and should be sped up by that inner scheduler, right? So there's these two things going on. So we wanted to generalize sort of that situation so that we could hook up scheduler components in different ways without having to create new abstractions or new kinds of abstractions every time. And John, I am so happy you're here because, I think about this in very simple terms. I'm not. So you saw, right, there was an arrow going in and an arrow going out, things going in and out. So it's not a monad, right? Monad, only things come out, was my thinking. But there's an underlying state going on. So you get like, this picture, right? So you've got, an alpha and a beta, and there's, I call this my metaphor for monads is there's a river of slime going on underneath. So there's a picture from Ghostbusters, and only when necessary you reach inside. So of course those are arrows, right? And everything worked out beautifully. On top of the fact that it gave us compositional scheduling policies, it also gave us a graphical notation, and that's something that customers had been asking about forever. They wanted to be able to graphically assemble scheduling policies, and nobody knew how to do this. Unfortunately, we never got to the point where we implemented it, but at least it was also a useful metaphor in just constructing these scheduler networks. I'm not usually a visual person, but here's a place where I actually used to draw pictures before I put them in code. So, so we ended up with this thing called the purely functional fab. Everything, I started out this code with some imperative parts, but I learned that really it is a good idea to keep everything pure, even in a hardcore industrial settings like this. So that was my second lesson. And it carried through, for example, to situations where I didn't expect it for the longest time. So I don't know if you were like programming GUIs like in the last century or even 10 years ago. A lot of GUI toolkits would follow like this, would have like an event loop and callbacks and things like that. And somehow I always thought, well, the next GUI has to be better than the last one because the last one I never liked particularly. And that opportunity came along in the form of an application on social pedagogy where a designer came in and redesigned our boring user, a really, really ugly user interface, and that required us to re-implement it. And we took one shot at this using the MVC paradigm, and it still looked like this. And we were very unhappy about this. And so that forced me to really look at why our GUI code always ended up like this. And I downloaded a picture off the internet that shows how model view controller is supposed to work. And there's these arrows. I have no idea what they mean, right? I don't know what the difference between the solid lines and the dashed lines are. But it looks kind of strange. It doesn't look quite right? It's not symmetric. And you can see, you can follow the arrows and go round and round and round. And one of the problems with MVC is, of course, that your events sometimes go round and round and round because your model causes a model change causes a change in the view. The change in the view goes back, causes a control, causes a change in the model, and so forth. And then you have to break that cycle. And that is one thing that causes really ugly code. I once showed this diagram at an OO conference, and he said, I have two of these things swapped, but I don't remember which ones. So anyway, the second problem is this, right? You have a model, which in your functional program is just going to be a value, and you want to turn it into a view. And computing that initial view is usually pretty easy. You just compose your GUI components according to the structure of your model, in some sense. But the problem is if there's a change to the model, right? And what you then need to do is you need to find the corresponding change in the view, right? Or vice versa. Somebody clicks on a button or something, you need to find the corresponding change in the model. So you sort of have to implement the mapping from the model to the view twice. Once for the whole thing at the beginning, and then for every delta that you have. And as your GUIs get more complicated, they're very easy to go out. It's very easy to make them go out of sync. And so that was the other problem. And then a couple of years ago, this thing came out of Facebook called React, which is a JavaScript framework. for GUI programming that looked like it's pretty close to the ideas of functional programming. It's not quite there, but close enough in many ways. And so I got really excited about this. I didn't get so excited about the fact that it's written in JavaScript. But one advantage of JavaScript is that it now really runs on almost every platform. So, I mean, of course, it runs in the browser, but for example, since Java 8, their fancy new GUI toolkit called JavaFX contains like one useful thing, which is called WebView, and there's an entire WebKit inside that one single widget, and everything else you can ignore. And similarly for Windows, of course, where JavaScript and HTML5 is a first-class citizen, but we didn't really want to program in JavaScript itself, and it was, it was like 80% functional programming, not quite there, but it turned out that we could make it go much further, at least, in the direction of functional programming by creating a wrapper around React, or using React as the infrastructure for our own GUI model, and that's called Reactl, and that's actually a Googleable term. We'll give you a piece of open source software that you might like. Anyway, and that gives you a different kind of model, meta model, where, well, you have the model. You write a function that will map it to a view, that will compute the view from the model. And if there's a change, of course, us being functional programmers and me wanting to keep things pure, you don't mutate the model in place, but you create a new model object, and which will generate a new view. And React is this magic piece of software which will turn that into efficient updates in the browser. And so we were able to use that. And we keep the callbacks are kind of traditional. We don't do much there. But due to the fact that you don't have that incrementality, already breaks the cycle. So this solves both of the problems that we often encountered with Model View Controller. So just to give you a very quick demo, somehow with these things, you always have to give like a to-do list as a demo. So here's one. So there's individual to-do items. Each one has a checkbox. Each one has a delete button and a text that describes what it does. And so here's a piece of Clojure script code. What you do is you really focus on what your model is without worrying about the GUI at this point. So there's a record declaration for an individual to-do item. It needs to have a number so you can distinguish it from others that have the same text. And then there's the text, and then there's the done flag, which is false in these two. So this is just corresponds to that picture. And there's these two to-dos, T1 and T2, and then you have sort of the entire application state where you just have the list of to-dos right here, and you have the next upcoming number. So you have like deterministic operation for those unique IDs. And what you then do is, well, so the tricky part about designing a toolkit for this model is to make it modular, right? It's pretty easy to sort of to generate like one big thing from your big model object that contains your entire application state. But what you really want to do is you want to write views for little things and then compose them rather than having to implement this monolithic thing. And it took us quite a while, and we implemented with lenses a little bit. Finally, we came up with what I think is quite a simple model where you declare what's called a class, which is, if you will, a type or a class of GUI items or widgets. And each class this is the GUI item that it can talk to during its runtime, and to-do is the application state. So that will be one of those individual to-do objects from the previous slides. And each class specifies a render expression. It's just a pure expression that will convert that app state into HTML. Now, this being ClojureScript, so it's a Lisp dialect, so it doesn't have like, the pointy brackets, but other than that, this is just standard HTML that comes out. And you might not like HTML and CSS, but there's a lot of great tooling that allows you to get it right. Well, you don't have to understand all of this. So this is just the same code with a couple of callbacks added to the buttons and the checkboxes. And what these callbacks do, I've got that enlarged here, is they usually send a message to one of those GUI components. And in the case when you click on the checkbox, it will just send true or false to a particular GUI component. And for that purpose, you have a handle message section in the class. And that is just a pure function again that will receive that message that says whether that item is checked or not. And it will return a value that just indicates I've got a new application state. And then the underlying machinery will take care of actually installing that in the system and updating the view. And that's a paradigm that's worked particularly well for us. So still got a little bit of time. Any questions for this? This was like the most technical part so far. Yeah, there's one.
Are
No, you can use any object you want, right? The idea is often in JavaScript applications, the original, like the JavaScript event objects, right? They travel quite far in a system, but they're really opaque and they're difficult to test because they're difficult to synthesize. So this separates the GUI logic from the application logic, was our idea, right? Is you extract something from the GUI that encodes the user's intention, and the handle message function then receives that intention and turns it into a change to the state. And this has wonderful testability actually, because you can actually test it independently of the browser. And I don't know if you're doing JavaScript development, but if you need to test JavaScript code, it's surprisingly nightmarish. And that makes large parts of that testing so much easier. You can do it as part of continuous integration, and you don't need like fancy tools. So it's really, really pleasant to deal with. Of course, that's a whole nother talk. Okay, so anyway, so this brought home once again the message of purity. And recent application that I just shipped a new version out from here was this. We had a client, or we have a client, that is a large automobile services provider in Germany. And what happens is periodically you need to drive your car to one of their shops. And your car goes into a lane in the shop, and then it gets subjected to various examinations. And so usually at the end of each lane, there's sort of a workbench or closet that contains a computer, a desktop. It used to contain a desktop computer and a printer and various devices that you can then hook up to the car to analyze it. And a couple of years ago, they said, well, we're going to transition to a situation where not every single lane has a standalone computer, but every employee is going to get a tablet. And employees actually move around the organization quite a bit, and they will just take their tablet with them. Now that creates a problem because if you push like the print button, this has like the organization has like an organization-wide LAN. If you push the print button and you don't reconfigure your printer as you move somewhere else, that printout will come out where you were and not where you are. And the same goes for network drives and other aspects of the configuration. So they wanted a system that would reconfigure the computer as you moved around in space and within the organization. And of course, this being auto shops, you don't, and people would also sometimes, if you have a Porsche or something like that, then they would send somebody out to the client. So you don't have ubiquitous network connectivity either. So we knew that we couldn't store the configuration information in a central database. But you only want to configure each printer once and each piece of hardware once. You don't want to have to do it for every single tablet. They have 1,500 of those tablets and a lot of lanes and a lot of things to store in the configuration. So our idea was this: every single tablet would know the configuration of everything in the organization, at least asymptotically, and they would just synchronize amongst each other. We're not really algorithms people, so we decided we're going to keep it simple. We're just going to implement pairwise synchronization, whenever two tablets sort of meet in the dark, and so they exchange information. And so the first thing when you do this kind of thing is you have synchronization among 1,500 machines, is you don't really want to remember, oh, last time I talked to this guy, especially because the operating system might get reinstalled. So you really want to have like a fresh communication every time two of these tablets meet. And so first of all, one smart idea is that you reorganize your database. Traditionally, you might just have a mutable database where you just say, well, at this particular lane, there's this printer configuration. The problem then is if there's a conflict, and if two people set different configurations, and maybe you can compare them by timestamp or something, but that is something bound to go wrong. It took us a while to realize that we were really building a very large distributed system, even though it doesn't sort of look like it. And all the usual things, all the usual lessons that apply to distributed systems applied in this setting. So really what you want to store is facts, things that happened. That person changed the printer configuration at that lane to this, and then you can have a conflict resolution strategy. And so then the problem of synchronization boils down of just you have one set of facts at one tablet, one set of facts at the other tablet, and you just want to make sure that each tablet gets the ones that it doesn't have yet. So you want to have like this. And of course, you want to have this be efficient because sometimes they just pass each other and then they go right out of connectivity again. So you really only want to transfer the blocks that the other side doesn't have yet. And so there's quite a great deal of literature on this, including great work by Ron there in the back. So we decided to take a very, very simple approach, which has worked very well, which is based on, I think, a lot of synchronization approaches in one way or another are based on Merkle trees. The way it works is this. You have your data blocks. Each data block gets assigned a hash, and some bits of that hash get used as a path in a tree, sort of like a radix tree or something like that. And at the internal nodes of the tree, you store composite hashes for all the blocks that are underneath. So if you will, each hash sort of summarizes the blocks or describes as a unique identifier for the blocks underneath. So that makes synchronization pretty easy in that, for example, you can just go from the top to the bottom of that tree. So you start with a top hash, and you compare the top hashes. And if they're the same, you already know, you're already done, because you know that both tablets have the same set of data blocks. And if they're not the same, you go down one level, you compare, the tree gets wider, of course, but maybe one subtree is the same and the other one isn't. So you can shrink it down again, and that process goes until you've reached the bottom of that tree, and then you can exchange the blocks. So since you're in Japan, this is like you're exchanging like business cards simultaneously at each step, which is very neat. Anyway, the code is not particularly interesting because it really corresponds directly to that idea. It's a bunch of F# codes, and since it needs to run on .NET, so you have the Merkle trees. Each block in the Merkle tree has a signature, which are the bits that denote the path. So each Merkle tree and each subtree has a prefix that leads to that subtree and a list of hashes and signatures of the blocks that are inside. And as you communicate during synchronization, you don't want to transfer the entire Merkle tree. You just want to transfer a fingerprint, which consists of that signature prefix and the composite hash of those blocks. And then during each round of synchronization, as you go down, you exchange these messages that say, I have fingerprints. And they all go sort of back and forth simultaneously until you reach the bottom when you say, here are a bunch of block hashes, and you need to transfer those to the other side. Now, the algorithm is purely functional, so that helps. That lesson is kind of obvious, but it helps to reinforce that every now and then. So you can put it in you can make a signature like this, which just characterizes a single round of that synchronization. And what's great is, again, that it is eminently testable, right? So you can just write a quick check test for this, and there's like one single quick check test that is important in the system, which just synthesizes, which just generates two sets of blocks, applies synchronization to them, and you hope, and in the end, you hope that the blocks that you have and the blocks that you receive are disjoint, and that their union is the full set of blocks. That's all, right? And that's been very successful at rooting out the few bugs that were left in the system. And when we started this project, I thought, the most complicated part of the system is going to be this synchronization thing. And surely we have to pay very close attention, and surely it's going to cause problems, and we're going to wake up sweating in the night. But the synchronization algorithm has produced 0 bugs since deployment a couple months ago. 0. So that was very gratifying. That doesn't mean we didn't have problems, right? On Windows, when you configure a printer, that is like nightmarish, and we're still working on that. Just mounting a drive, there's 3 different APIs, one of them secret in Windows that do this, and you need to use a different API for mounting and unmounting for that to be reliable. Just generally tracking a changing environment. We made the mistake of not using Reackle for the GUI and instead using that XAML thing that they have for WPF on Windows, which is another nightmare. We thought it's going to be a real simple GUI. It just displays a bunch of buttons. You push one where you are. But that turned out to be unnecessarily hard also. And of course, all of these things have to do with mutable state. And that's also been, I could enumerate a lot of projects where you really see that the purely functional parts usually cause very few problems, and most of the problems are in the parts that have mutable state. So again, I'm preaching to the choir. Sorry about that. But there you go. It's just a retrospective. It's supposed to teach you lessons that you already know. So functional programming has been, in my experience, has been eminently successful in efficiently implementing all kinds of software projects. And I showed you a range from social pedagogy to semiconductor fabrication. And they actually have some common parts. So that's really nice. So use functional programming. It is always better. And in fact, whenever I've been programming I've been programming using functional programming for a year, and there's like a little piece of object-oriented programming I need to do because for whatever reasons, I find out that it's worse than I remembered, like much worse. And somehow my memory mellows, right? And even now, I'm really, how bad can it be programming in Java? Pretty bad. Pretty bad. Anyway, so a lot of the functional programming languages that we know support imperative programming as well, right? But even when you have it, it's a good idea if you can get by without using it. Even even in applications that seem inherently stateful. So one of the sobering lessons of that semiconductor fab thing, this is about simulation, right? Wasn't object-oriented programming originally created to do simulation? So that seems to be like, it seems to be singularly bad for this particular application, object-oriented programming, right? And functional programming is pretty good. One reason why purity in functional programming is good is because it enables you to be systematic in your software development. And I talked about this at length on a tutorial here on teaching functional programming, where it's eminently important that you stress how to be systematic, because if you're not systematic, it's difficult to tell somebody, here's how you do things. And of course, that is just as important when you do actual software development. Part of that same approach, when you're being systematic, part of being systematic is really you should do your development using types in your thinking, right? The Clojure people, they've done great work, but they haven't quite caught on to this idea yet. I don't know if there are any in this room, probably not. So that's important. Use types in your design. Static typing, I could go on at length and bore you. We've had successful projects using both statically typed and dynamically typed languages. My main gripe with it, of course, static typing has all the positive qualities that you all attribute to them, all of them. My main gripe with static typing is that at the type level, it's difficult to be systematic all the way through. And I think you've all probably found yourself in a situation, especially if you're Haskell or especially if you're Scala programmers, where you've written a perfectly correct program and it's perfectly type correct, but the compiler won't believe you. And you've done a significant amount of tinkering to convince your compiler of the type correctness of your code. And I wish that would be more of a criterion that we apply to type systems, is that they really enable systematic programming. And with that, I close. Thank you for listening and staying so long.
I'm curious, so you said that functional programming is always better, and I'm a big fan of functional programming, obviously. But I'm curious about the cases where perhaps you can't afford a intermittent GC hit or something along those lines, where actually the real-time aspect is very important. How you might approach that with functional tools.
So admittedly, we haven't encountered those applications yet, and we might in the future. I mean, much like the situations that you encounter, right? My personal belief is that may be a matter of existing tooling, right? So I'm very much convinced that functional programming is a great tool for that. Just at Farm, we had a great talk on how to use functional programming on an Arduino. So somebody's getting there and thinking about those issues. But for if you have like a really tiny platform and you really need to worry about memory consumption, things like that, then you might not have the tooling yet to do that. But I'm sure we will have in the future. So as I said, I don't think that's a restriction of functional programming. It's just a restriction in the tools that we have at this point.
Oh. Okay. Anyway, I just go ahead. Just as an answer to that one.
Sorry, where are you?
Matthias, here.
Hi.
So basically, if functional programming and the types you have don't help you enough, of course, the answer is always more types. And then you do like linear typing and stuff like that, and region typing, and then you can control your resource usage. But yeah, you need tooling for that.
Yeah. So Ron's going to talk about, or you could talk about allocation-free functional programming, right, to address part of that problem.
Yeah, although it's closer to like strongly typed allocation-free imperative programming.
Sure. Okay.
But I actually wanted to ask a different question, which is, I wonder so part of the kind of React framework is an approach to kind of efficient incremental updates of your view. And part of that is what goes on in the virtual DOM, and part of that is what goes in the computation of the virtual DOM.
Yeah.
And I'm sort of wondering whether you guys did sort of anything interesting and anything different from, like, basically the basic React model there is based on equality, where you sort of check that like your inputs are the same as they were before. And equality is a kind of fraught concept and easy to get wrong and a little confusing in spots. And you can make mistakes where you specify your equality not quite right, and you can get weird path dependencies in your UI where you get stuck in a weird state because you didn't encode your equality correctly. And I know there's a lot of weird corner cases there, and I'm just wondering if you did anything interesting in that space.
No. And to be honest, so that made me worry when so that's actually relevant for the layer that we put on top of React, right? A lot of that is really about that equality. But we got it to the point where it works. And we've had a little brief exchange on Twitter, and we really don't think about this GUI thing in terms of incremental updates. And I think that's a major philosophical difference. I really want to think about it in terms of there's a new model, somebody else figure out whatever incremental thing, that works for us.
Yeah. For what it's worth, I suspect we agree. I think it's.
Huh?
I suspect we agree. Actually, we also think about it in terms of pure functions.
Yeah.
It's just a question of how you optimize those pure functions.
Yeah, sure. So there's lots of ways where you can imagine that you could do better performance-wise, right? But for us, even for very complex and like very big UIs, those have tended not to matter as much as you would think. So I can easily see that you can do better. For us, this is enough. Right.
Chaz from X. I don't know how much you count their approach as functional, but Galois has a tool called Atom and some stuff built around it for doing embedded systems and a sort of Haskell EDSL. Mm-hmm. And their general approach to handling the resource issues is just to generate C code.
Yeah.
So if that's something you're interested in.
Yeah, we've done one of those. We've done a very similar project as well that would generate C code or SCADE code or something like that. That's a viable approach, but it doesn't feel quite satisfactory. Is always my when I do this, it doesn't feel quite right. But it's certainly better than just doing your programming in C or in SCADE or whatever by hand. Yeah.
I really enjoyed your talk, but I'm wondering, have you ever given it to a room of object-oriented programmers?
Bits of this, plenty of times, yeah. Maybe another lesson that's really unrelated, but I think 10 years ago, Manuel Chakravarti at some FTPE workshop said, "Don't say the M word." I think we've gotten into this culture where we've gotten into this situation where a lot of people think that by giving monads a more approachable name, whatever that means, we're going to make everything easier. And I personally don't think that is so my personal experience has been that is not the case at all. That really people who tell you that saying monad is going to make things less approachable, they really don't want to be approached for other reasons. On the other hand, monad is now a perfectly fine thing to say at Java conferences. It has been my experience. Of course, monads are in Java 8 now. They don't have a name, but if you give them a name. Even in Germany, who's from Germany in this room? Oh yeah, big contingent. You actually both, does anybody live in Germany from those Germans? No. So see, there you go. So at ICFP, we've seen functional programming get big in like all kinds of countries, except for Germany. I think all the Germans that have been here mostly have been my personal friends. So even there, where functional programming is like 5 years back from wherever you live, right? People generally have heard of it. They generally know that it is better. You don't need to convince them anymore. You really just need to tell them how it works. And so these kinds of talks and even substantially more technical talks on functional programming work just fine with your average, whatever that means, OO developer. Hardcore OO developer is maybe a better word.
Okay. Let's thank Michael for his talk.
Thank you.